Okay, so in this problem we have a ball of mass little m, which strikes a homogeneous bar of length L and mass capital M at distance h from the pivot point O. Given this information, we're asked to determine the distance h such as the horizontal reaction force of the bar at point O is 0. And in reality, this position h is often known as the object's center of percussion, and this has been used somewhat famously in the sporting goods world to try to minimize the amount of reactions that would occur when striking a ball, for example, with a bat. Though to be honest with you, the commonly known sweet spot is typically somewhat removed from the center of percussion in practice. So the way I'm going to work this problem is I'm going to note that because I'm looking for a distance associated with a force, it makes sense to treat this as a Newton's second law problem. And in this case, I'm not really going to worry about the impact event so much as just saying where that impact force is going to occur. So if I draw a free body diagram of the system, I'm going to have here reactions at O, which I'll call OX and OY. Of course, assuming that we use a conventional XY axis set. And we will, of course, have the weight of the bar, which will be capital M times G, and we'll have some load here due to the impact, which I'll call F, located some distance down the bar. Now we know post-impact this thing can have an acceleration at center of mass in the x and y direction, so I'll have here capital M times AGX. We'll have also some capital M times AGY, and we'll know that this bar has the propensity to rotate post-impact, and I'll call this I about G times alpha. So now that I have that in place, I can go ahead and write down my kinetics equations for this problem. And so if I do that, I can first of all sum forces in the x direction, set that equal to m times agx. And if I do this here, what I'm going to have is OX plus the applied force F is going to equal m times agx. And we can call this equation 1. I can also sum forces in the y direction and set that equal to m times agy. And if I do this here, I'm going to have OY minus mg is equal to m times agy, and we can call that equation 2. I can also sum moments about point G and set that equal to I about G times alpha, or in this case, maybe easier to do is to sum moments about the fixed point O and set that equal to I about O times alpha. I can do this in a counterclockwise positive sense, and if I do this and work this out, the only force that's going to contribute a moment about O is going to be the force F, and we know that's going to create a positive moment with the distance associated with it of h, and that's going to equal, in this case, I about G plus the distance between, I should say the mass of the bar, times the distance between O and G, which is going to be L over 2 quantity squared, and that's going to be times alpha. Now if you use that I of G is equal to 1/12 ml squared, this is going to work out to be 1/3 times capital M times L squared times alpha, and we can call this equation 3. Now if we look at the three equations we recovered from kinetics, you'll note that we have 1, 2, 3, 4, and 5 unknowns. And so we're going to need some additional equations from kinematics to help us out here. And so in this case, what I'll do is I'll say, well, I can know that the acceleration of point G is going to equal the acceleration of point O plus alpha across r of G with respect to O minus omega squared times r of G with respect to O. We know that previous to the impact event, there is no angular velocity, so we can set this equal to 0. And so what we'll be left with here is that agx in the I plus agy in the j is equal to AO, which is 0, plus alpha in the k across r of G with respect to O, which is minus L over 2 in the j direction. If I note that k cross j is minus I, this means I'm going to have this is equal to alpha L over 2 in the I. If I break this into components, I'll have here in the I direction that agx is equal to alpha L over 2. We can call this equation 4. And if I look at the j component, I'll have that agy is equal to 0. We can call this equation 5. Now if I take these two results and plug them back in, because I'm going to work this one all the way out for you, if I look at equation 1, I'm now going to have that OX plus F is equal to alpha times capital M times L over 2. And if I look at equation 2, I'm going to have here that OY minus mg is equal to 0. And I also, of course, know from equation 3 that F is equal, F times H is equal to 1/3 times m L squared times alpha. So I can take equation 3 and I can solve for alpha, and in this case I'll have alpha is equal to 3 times f times h divided by capital M times L squared. And I can take that result and plug it back into equation 1. So equation 1 now is going to give me that OX plus F is equal to M times L over 2 times alpha, which is 3FH over ML squared. We can do a little work here. Note we're trying to find H such that OX goes to 0, so this will go away. The mass will cancel out on each side. The H1L is going to cancel out. And so what I'll be left with here is on the right hand side, I'll have 3 times F times H over 2. I can then cancel out a F from both sides. And if I do that, I'll end up here with the result that 1 is equal to 3H over 2 times, sorry, there should be an L in the denominator here as well, which of course means that H is equal to 2/3 times L. So for this nice uniform bar, this is going to locate that center of percussion for us. And so if you always strike that bar 2/3 its length away from the fixed point of rotation, you'll actually get 0 net reaction in the x direction. A very interesting fact, and one that can be used in practice and is used extensively. Alright, with that, I'll go ahead and wrap us up and simply wish you the best of luck. Take care, everyone.